Hello, and welcome back to the Umbrella Academy. Organic reactions where two atoms or groups are removed from the molecule to form a product is called elimination. Various types of elimination are 1 elimination, which is also called alpha elimination. In this type of elimination, both atoms or groups are lost from the same atom to give a carbene or a nitrane. For example, consider this molecule, in which X connected to B, leaves along with the bonding electron pair, and the bonding pair between B and W, is retained on B to form a carbene or nitrane. Second type of elimination is 1-2 elimination, which is also called beta elimination. In this case, atoms or groups are lost from the adjacent atoms to form a new double or triple bond. For example, in this molecule, leaving group X leaves along with bonding electron pair, and the bonding pair of W. A bond is retained between A and B to form a new pi bond. Atom B is attached to leaving group denoted as alpha, and the atom A is directly connected to alpha position and is denoted as beta. Third type of elimination is called gamma elimination. In this case, atoms or groups are lost from atoms which are two or more than two bonds away. This usually leads to cyclization. For example, in this case, atoms are lost from carbons, which are two bonds away, and leads to formation of a three-membered ring. Our lecture is based on beta elimination, also called as 1-2 elimination. This can be divided into two types. One type taking place in gas phase, also called as pyrolytic elimination. The other one largely taking place in solution. In case of reaction in solution, nucleophage or leaving group leaves along with the electron pair. The other atom or group leaves without its bonding pair, most often being hydrogen, which is abstracted by a base. Beta elimination in solution mostly leads to the formation of new C-C double bond or C-C triple bond. This happens by any of the three types of mechanisms: E2, E1, or E1CB. We will discuss E2 mechanism first. Consider this molecule. X is leaving group here. This carbon must have hydrogen attached. This is called alpha carbon, and the immediately attached carbon is called as beta carbon, which has hydrogen attached. Base abstracts this beta proton, so that its bonding pair is retained to form a double bond between alpha and beta carbon. And at the same time, X leaves along with the bonding pair. This results in the formation of a new pi bond between the two carbons which lost the two atoms. It is obvious that this is a one-step mechanism. Two groups depart simultaneously, with proton being pulled off by a base. Therefore, this only step must also be the rate-determining step. Therefore, mechanism must be kinetically second order. First order in substrate and first order in base. This is obvious, because rate-determining step involves both substrate and base. Since two molecules are involved in RDS, it is called E2 mechanism, elimination by molecular. The base used may be neutral or negatively charged. We can write the rate equation as rate equal to rate constant K times substrate concentration times base concentration. It means, doubling the substrate concentration doubles the rate. Likewise, doubling the base concentration doubles the rate. Doubling both substrate and base concentration makes rate 4 times. If we plot rate against substrate concentration, we will get a straight line because rate is first order in substrate concentration. Similarly, if we plot rate against base concentration, we will get a straight line, as the rate is first order in base concentration. The most compelling evidence for the E2 mechanism is found in stereochemical studies. E2 mechanism is stereospecific. Which means, stereochemistry of the product depends on the stereochemistry of the reactant. To understand this, let us write the substrate again. The base abstracts the beta proton, the bonding pair of proton and beta carbon moves to form a pi bond between beta and alpha carbon, and the leaving group leaves from alpha carbon along with bonding electron pair. For this, we can write a transition state like this, in which bonds being broken and bonds being formed are at intermediate stage and are shown in red dotted lines. Ultimately it leads to alkene product. If we focus on this transition state, we can see that 5 atoms involved in bond breaking and making, including the base, must lie in one plane. Which means that, alpha carbon and leaving group bonded to it, beta carbon and the proton bonded to it, as well as the base that is going to abstract this proton must lie in one plane. There are 2 ways for this to happen. One way is, this arrangement, in which H and X are trans with dihedral angle of 180 degrees. Another way is, this arrangement, in which H and X are cis to each other with a dihedral angle of 0 degrees. These are sawhorse projections, and can be converted into Newman projections for easy understanding of cis and anti-relationship of H and X. So, sawhorse can be drawn as Newman projection like this: the hydrogen on front carbon goes up, and X on back carbon, goes down with dihedral angle of 180 degrees. This is called anti-conformation. Similarly, this sawhorse can be drawn as Newman projection like this: both hydrogen on front, and X on back carbon goes up. And this is called eclipsed conformation. This one is called anti-coplanar arrangement. Whereas, this one is called syn-coplanar arrangement. The anti-conformation is lower in energy because it is gauche anti-conformation. Whereas, this eclipsed is no doubt higher in energy than anti-conformation. We will now show the orbital diagram of concerted transition state in E2 reaction via anti-coplanar and syn-coplanar pathways. In the anti-coplanar transition state, the CH and CX sigma bonds are coplanar, but on the opposite sides of the C-C bond. As the bonds break, the carbons change hybridization. The sp3 orbitals change to the parallel p orbitals, which then overlap to form the pi bond. This is staggered conformation, with base far away from the leaving group. In most cases, this transition state is lower in energy. In the syn-coplanar transition state, the CH and CX sigma bonds are also coplanar, but on the same side of the C-C bond. As the bonds to hydrogen and leaving groups start to break, the hybridization at each carbon begins to change to sp2 and the remaining p orbitals start overlapping to form the pi bond. This is an eclipsed transition state. In addition to the higher energy resulting from eclipsing interactions, this transition state suffers from interferences between the attacking base and the leaving group. To abstract the proton, the base must approach quite close to the leaving group. In most cases, the leaving group is bulky and negatively charged, and the repulsion between the base and the leaving group raises the energy of the syn-coplanar transition state. Thus, out of these possible conformations, the anti-coplanar arrangement is most commonly preferred for E2 elimination. Thus, if beta carbon has one hydrogen only, then, only one alkene can be obtained as product via anti-elimination. This is because, there will be only one conformation, in which groups to be eliminated are anti. Thus the particular alkene isomer obtained as product depends on the structure of the reactant. This is the origin of stereospecificity in E2 elimination. Remember that, this requirement of coplanarity is not entirely absolute. Small deviation from coplanarity can be tolerated. If proton and leaving group are nearly planar rather than being exactly coplanar, it is called periplanar. Thus, for E2 reaction, if the groups are not exactly anticoplanar, then anti-periplanar arrangement is sufficient for E2 elimination. For example, a dihedral angle of 178 to 179 degrees is okay. This requirement of anti-periplanar arrangement will determine the stereoisomerism of the product. In other words, we can say that, stereoisomeric product of an E2 reaction process depends on the configuration of the starting alkyl halide, hence making this stereospecific. Thus, this alkyl halide has required anti-arrangement of H and Br. Red-colored R1, on both carbons are on solid wedge, meaning they are on same side, and green-colored R2, on both carbons are on dash, meaning on the same side. Thus, elimination gives cis-alkene. Similarly, in this second example, H and Br has required anti-arrangement for E2 elimination. Red-colored R1 on both carbons is opposite, so are the green-colored R2 on both carbons. Thus, elimination gives trans-alkene. Consider this molecule. Number the carbons 1 to 4. Absolute configuration of carbon 2 is S, and that of carbon 3 is also S. Therefore, we write this molecule as 2s3s. Upon elimination of HBr, we get this alkene, which certainly is E-alkene. Take this second isomer. The groups at carbon 3 are oriented to make this R. So this becomes 2s3r. Upon elimination of HBr, it gives alkene product, which is Z-alkene. We will understand the elimination mechanism of these two isomers to give different alkenes as products. Take this 2s3s isomer first. Convert this Fischer projection into Sawhorse projection. Remember that Fischer projection is always eclipsed, and we have converted it into exact eclipsed Sawhorse. If we see molecule from this side, we can write the Newman projection like this, in which groups on front carbon eclipse onto those on back carbon. For elimination to take place, leaving group and beta hydrogen must be anti. Therefore, we rotate the back carbon by 60 degrees, so that red bromine is exactly anti to red beta hydrogen. Now remove the molecule of HBr, we are left with this, in which phenyl and H is on one side, and two methyl groups on other side. We can draw the molecule exactly as it is. And we see similar priority groups are on opposite side of double bond to make it E-alkene. Now take another isomer designated as 2s3r. Convert it into Sawhorse projection. Remember, we converted eclipsed Fischer into exact eclipsed Sawhorse. Now we will convert it into exact eclipsed Newman projection. Red beta H and red alpha Br are exactly eclipsed in this conformation. So, we need 180 degrees rotation of one carbon to make the required anti-arrangement of Br and H for elimination. After such a rotation of back carbon, now H and Br are anti. Remove the HBr molecule. We now get this product, in which phenyl and methyl are on same side, and methyl and H are on same side. Redraw this molecule, and check out that this turns out to be Z-alkene, as the similar priority groups are on the same side across the double bond. Thus, the isomer with 2s3s configuration gives E-alkene as product after E2 elimination, and the isomer with 2s3r configuration gives Z-alkene as product after E2 elimination. Thus, this proves that E2 elimination is stereospecific. This stereospecificity is because of the requirement of anti-coplanar arrangement of groups being eliminated. Sin elimination is not found to any significant extent, unless anti-elimination is greatly diminished by failure to achieve the 180-degree dihedral angle, for example in rigid systems. We will see some examples of this later. If you don't want to miss out important lectures, then subscribe and press bell icon for notifications of new lecture uploads.